Okay, so now let's take a look at what we could do if instead of trying to estimate mean from one population, we've got two different populations and we want to estimate what is the difference in the means between these two populations. So we've seen plenty of problems like this in the past. So now we're going to assume that we've got two different independent random variables. That's important here, that these are independent random variables. Where x is from a normal distribution with unknown mean and unknown variance. Y is from a normal distribution with unknown mean and unknown variance. So in order to construct these interval estimates, it's going to be useful to know what the sampling distribution for these things looks like in theory. And so let's assume that we pick from population X a sample size N1, and we pick from population 2 a sample size N2. So what I would like to show is that the expected value for the difference in the means is actually the difference in the two population means. And secondly, what I'd like to show is that if I want to measure the width of the sampling distribution of x bar minus y bar, I can calculate the variance of that distribution. And in fact, it's going to come out to be some combination between variances of the two distinct populations that we have. So for the expected value, this is going to follow something similar that we've done. So I want to calculate the expected value of this difference. Because these are independent, I could split this up to be the expected value of x bar minus the expected value of y bar. And we know what each of those are, but just for the sake of being detailed here, x bar would be the sum of the xi's from 1 up to n1, all divided by n1. And the expected value for y bar would similarly be the sum of all the y's for j going from 1 up to n2. Let me get that subscript n sub 2. And we're going to divide all of that by n2. And so we can pull out the 1 over n, and then we're going to sum n1 times. All of those expected values are the same since they all come from x. And over here, we can pull out the 1 over n2 from inside the expected value. And what's left is n2 times the expected value of y. And these constants, the n1 and the n2's cancel. So what's left is the expected value of x minus the expected value of y. In other words, mu x minus mu y. And so let me just say that we've already seen the expected value of x bar is mu x, and the expected value of y bar is mu sub y. So we could have just said from this stage, well, we've already seen that is mu x, and we've already seen this is mu sub y. Okay, so now let's try and prove this statement about the variances. And so with variance, keep in mind that we're calculating the expected value of something squared. So when I break up the difference here, it's going to be the variance of x bar plus, and when we pull out that constant minus 1 in front of the y bar, we square it. So we actually get minus 1 squared times the variance of y bar. And so the variance of x bar, that's sigma squared x bar. And now the minus 1 squared becomes a positive 1. So that's why we actually add these two as opposed to take the difference. And then from the central limit theorem, we've already seen that the variance for x bar is going to be sigma x over the square root of n1 squared. And the variance for sigma y bar is going to be sigma y over the square root of n2 squared. And so when we square both of those, we get exactly that the variance of the difference of the means is equal to the variance of x over n1 plus the variance of y over n2. So this is going to be a useful property when we want to estimate the standard error for the distribution of the difference in sample means. Okay, so let's use this information about the sampling distribution for a difference in means now to come up with a method for constructing a t-confidence interval for a difference in two independent means. So now I've got random variable xi's that are coming from one normal distribution, and we've got a sample size n1, and then we have a second batch of values that are picked from a different normal distribution, which is independent from the first. And we're going to pick n2 values from that for that sample. And what we want to do is approximate the mean of the difference of population means mu1 and mu2. So we're going to take a similar approach. So the cutoffs for this are going to be equal to, we're going to start our estimate with what is the difference in our two sample means, and then we need to build some margin of error into that estimate. So recall that this stuff over here is the margin of error, and we're going to use the fact that the variance we just proved in the previous slide was equal to the variance of the first population over n1 plus the variance of the second population over the sample size of that. And since we don't know what these variances are, we use the two sample standard deviations. And since we don't know what the variances are, that's why we use a t-distribution again. So it pretty much looks exactly like what we did for a single mean, except now our statistic that we start with is the difference in our sample means, and we're going to adjust the standard error to use this new formula to estimate the standard error. The t alpha over 2, that's the same as before. And so one thing that we need to be careful about is that when we found this t alpha over 2, it depended on how many degrees of freedom do we have in the problem. And that depended on how large was your sample. But now we've got two samples, n1 and n2. So how do we find out what the right degrees of freedom would be to use for this t-distribution? So we'll kind of talk about it. First, if you're not using technology, then informally, it's not too bad of an estimate to pick the smaller of the sample sizes and use that as the basis for calculating the degrees of freedom. So I would say which of these two is smaller, n1 or n2, and then my degrees of freedom are going to be the smaller sample size minus 1. That's a rough approximation. We can get a slightly better estimate for how many degrees of freedom using what's called Welch's approximation. This is not something I would ever ask you guys to calculate by hand. So this is something that there's a nice formula for it, and R has built-in capability to do this when you run a t-test in R. But in case you're curious about where the degrees of freedom come from in R's calculation, it comes from using what's called Welch's approximation. And so when we're working with estimate for difference in two means, usually what we're interested in is whether or not there seems to be some difference in these two means. And so when we're interpreting our confidence interval at the end, what we might want to look for is whether or not 0 is inside of our confidence interval. And so if the value 0 is inside of our confidence interval, then that would be a plausible value for the difference. So in other words, when 0 is inside of our confidence interval, we can't be certain that there is a difference between these two means. If our confidence interval contains only positive values or only negative values, then that gives us a pretty good indication that there is a difference between these two population means. If we're working with really large data sets and we don't want to do these calculations by hand, then again, we can still use the t.test command in R the same way we did it with one sample, except now we would enter where is your first data set, what is your second data set, and the rest of it would be the same.